So this was one of the highlight notes in physics this year. Or you could say in science, really, in this year. We had a new, better measurement of one of the constants in nature. Okay, and it's called the mu on G factor. Well, we want to help understand in this presentation, in this video, what that new news means, and also, relate it compared to the prediction we just published in March. All right, so the standard model has been using this number as a prediction. It's kind of the standard model doesn't predict any of the constants in nature, right? But they found a way to put together something close to what they're measuring, and this is the number they've been using. Notice it has error bars because it's coming from error concepts. Anyway, this is the number they've been using, and this is the number we predicted out in March. And in April, just right after that, the Fermilab came out with a better measurement, okay? Really cool news, right? I mean, anytime you get a better measurement of one of the constants in nature, it's a big deal because those are the things we've got our best measurements of already. Those are the things we know the most. So if you improve that, you actually push your ability to understand reality in a particular way at that point, right? To look at it. You've seen it sharper than you ever have before. So really cool news, but I want to help understand the comparison between these numbers, because just throwing these numbers up is probably just Greek to everybody, right? So let's compare the numbers. We notice the first digits are all the same in here, so we have a unanimous agreement in all three of these here between those first digits, okay? But then the standard model is off on this digit, which is 1, 2, 3, 4, 5, 6, 7, 8 on the ninth digit. The standard model is now off, okay? And from there on, of course. And this is, well, you can see the difference there, but I want you to see it pictorially now. Instead of having the numbers in front of your face, we're going to just say standard model has a value here. We'll throw it on a number line somewhere, but now we show you the error bars of its value, okay? So it's somewhere between there according to the standard model. The Brookhaven measurement, the older one, had a measurement predicting there with error bars that stretched out to there. Cool. Okay, so you can see the problem here is already a little bit of gap. But remember from before, the gap's way out at digit 8 where this is coming in, okay? How do we understand if this is a real problem? If that size of a gap is okay, or if it's too big, how do we know? Well, here's the standard way. It's a comparison of the error bars itself. So if you multiply it 2 times, then that's the error bars 2 times, then that's the range in which we're 95% confident. The true number has to be within that range, and we're 95% that that's correct. I think a lot of scientists are pretty happy with the 2 sigma ranges where we just stick it. But the 5 sigma is the official. If something's 5 sigma off, then it's definitely wrong, right? Well, if it's been the standard, it takes up to 5 for everyone to say, no, you can't. So we have a gap here, but this gap hadn't been traditionally enough to throw it out, especially because what are you competing with? Okay, now let's go a little bit further here. Let's stretch it 3. You see it's about 4 times just until we get into the very edge of where that number could be, okay? It's not 5, but it's 4. Here's our new measurement. So just our recent measurement here, you'd say, all right, well, isn't that better news for the standard model, right? It's closer, so good news for them. Yeah, you'd think that naively, but when you add the error bars, you notice that the error bars of this new measurement are smaller than the error bars of the old measurement, which means we now have 2 independent measurements, different machines and everything, right? Different people and different error bars, but with the independence and the tighter error bars, this actually means that the gap is larger. The red zone there between these two grew a little bit, okay? And this is ignoring the fact that we now have 2 independent measurements. If we only care about the blue one now, the Fermilab, the new one, the gap increased, okay? But when you include the fact that we have 2 independent measurements over here now, our confidence interval is this range. We expect the experimental average of our 2 great measurements now are in this zone, okay? And that's basically it. That's now where you want it to be, which makes it even worse for the old measurement. That's the news, okay? That's the point. Well, the number we had predicted is right here. Safely right in the experimental average, right? Beautiful, beautiful. And more important, notice I give a little thickness to the line there just so you can see where it is, but that's a line with no thickness. That's an exact geometric prediction out to any digit you want, okay? Beautiful. And what is that prediction? Last comparison, the numbers real quick, okay? Now we'll take our number. I have a ... there. What if you wanted to know what the next digit was? Well, this is the geometric arrangement, expression of this action, right? This is what we're calling when we, this is what we're addressing when we say the mu on G factor, this specific arrangement of boundaries in reality. So if all these terms are entirely foreign, we'll just parse them out a little bit. We have the volume of the hyperbolic figure 8 knot, this V sub Fe. That literally just represents that volume complement, and it's a constant like pi. It's a number. I'll switch the numbers real quick. It's that number. Okay. The next one here, alpha Feigenbaum constant. This is the geometric constant for things that split, hyperbolically split. Okay, beautiful. And then we have the Planck length, Planck mass, and Planck charge boundaries. So we have this fixed terminal relationship between those boundaries. And what do we have left? We have the red N, the blue B. So N is the 5 unique rotations that partition the hyperbolic figure 8 knot, and B is the break and scale symmetry of its inner construction. That's the whole picture, and that gives you you can pick any digit you want, and here's, of course, the numbers for those constants. Okay, so anybody can now go online, say go one Wolfram alpha, you have all the numbers, you have all the value, check, make sure it works, right? And yeah, there's a prediction all the way out. And here it just comes from this simple geometry. All right, that's cool, that's the news, and of course we're going to be given much more detail in the upcoming book, but there's the little snippet.